In this lecture video, we're going to learn how to multiply and divide radical expressions, including rationalizing the denominator. When we multiply two radical expressions together that have the same index, such as the nth root of x times the nth root of y, we can rewrite this as the nth root of the product of the radicands, x and y. Similarly, when we divide two radical expressions with the same index, the nth root of x divided by the nth root of y, we can write this as the nth root of the quotient of x and y. We learned these properties in a previous lesson, but they apply here as well. Let's take a look at 6 root 12 times 5 root 15. We'll begin by simplifying each of these radicals. 12 is divisible by 4, which is a perfect square. So we'll write this as 6 times the square root of 4 times 3. 15 is not divisible by any perfect square, so we will simply leave it as root 15. The square root of 4 is 2, so this becomes 6 times 2 times root 3. And with 6 times 2 equaling 12, we have 12 root 3 times 5 root 15. Now let's multiply the 12 and the 5 to have 60, and let's multiply the radicands. We have the square root of 3 times 15, or the square root of 45. The last step is to simplify the square root of 45. 45 is divisible by the perfect square 9, so we'll write this as the square root of 9 times 5. The square root of 9 is 3, and multiplying, we have 180 times the square root of 5. Now let's look at this next expression. Here we will assume that all variables are non-negative. Let's begin by simplifying each of these cube roots separately before combining them. Looking at the cube root of x to the fourth y squared z, x to the fourth is divisible by the perfect cube x cubed, with one factor of x left over. Y squared is not divisible by a perfect cube because 2 is less than 3. And the same is true for z. So in effect, we have a factor of x that comes out of the cube root, and we are left with an x y squared z inside the cube root. Now looking at the cube root of x to the 8th yz to the 4th, x to the 8th is divisible by the perfect cube x to the 6th. 6 is the largest multiple of 3 that's less than or equal to 8, and we have two factors of x left over. Y to the first is not divisible by any perfect cube because 1 is less than 3. But z to the fourth is divisible by the perfect cube z cubed with one factor of z left over. Now we can bring some perfect cubes outside of the cube root. The cube root of 6 is x squared since 6 divided by 3 is 2. And the cube root of z cubed is simply z. This leaves factors of x squared, y, and z inside the cube root. Now let's combine these two rational expressions. Our factors outside of the cube root are x cubed and z. Inside the cube root, we have 3 factors of x, or x cubed, 3 factors of y, or y cubed, and 2 factors of z, or z squared. X cubed and y cubed are both perfect cubes, and with a factor of x and a factor of y outside the root, this leaves a z squared inside the root, and simply x to the fourth yz outside the cube root. And that will simplify this product of two rational expressions. An alternative route could be to combine the two rational expressions first, and then pull out all perfect cubes at the same time. Both of these methods have the same result. They simply take a different route to get there. In this situation, the second route proved to be a lot quicker, but it's often beneficial to simplify each radical before combining. In example 2, we're going to multiply a radical expression, 8 times root 6, by the difference of two radical expressions, 5 root 2 minus 9 root 3. We will use the same distributive property that we've used before. We begin by finding the product of 8 root 6 times 5 root 2. 8 times 5 is 40, And we'll have the square root of 6 times the square root of 2. Next, we have 8 root 6 times negative 9 root 3. 8 times negative 9 is negative 72, and we have a root 6 times root 3. Multiplying these radicals together, we have 40 times the square root of 12 minus 72 times the square root of 18. Now we need to simplify the two radicals. The square root of 12 is divisible by the perfect square 4, so we'll rewrite this as the square root of 4 times 3. 18 is divisible by the perfect square 9, so we'll rewrite this as the square root of 9 times 2. The square root of 4 is 2, so this becomes 40 times 2 times root 3. And the square root of 9 is 3, so this becomes 72 times 3 times the square root of 2. And simplifying one last time, we have 40 times 2, or 80 root 3, minus 72 times 3, or negative 216 root 2. In example 3, we are now multiplying two factors, each with two radical terms in them. And we will use our same distributive property. We begin by multiplying 9 root 2 by root 2. This gives us 9 times root 2 times root 2. Then we have 9 root 2 times 3 root 3. 9 times 3 is 27, so we have 27 times the square root of 2 times the square root of 3. Distributing negative 4 root 3 to both terms in the second factor, we have negative 4 root 3 times root 2, or negative 4 root 3 times root 2, and negative 4 times 3 root 3. Negative 4 times 3 is negative 12, so we have negative 12 root 3 root 3. Let's simplify each of these terms. We begin by looking at 9 times root 2 times root 2. But what is the product of root 2 with itself? This is the square root of 2 times 2, or the square root of 2 squared, which is simply 2. So this becomes 9 times 2. The same can be said for the square root of 3 times itself. Root 3 times root 3 is root 3 squared, or simply 3. So this term becomes negative 12 times 3. In the middle terms, we have a root 2 times root 3. So we have 27 times root 6 minus 4 times root 6. Simplifying, we have 9 times 2, or 18. We have 27 root 6 minus 4 root 6, or positive 23 root 6, and negative 12 times 3, or minus 36. Adding, we have 23 root 6 minus 18. A property that we notice during this multiplication process is that when we multiply a square root by itself, we end up with the radicand. That is, for any non-negative value of x, the square root of x times the square root of x is simply x. We had the square root of 2 multiplied by itself, which gave us 2, and the square root of 3 multiplied by itself, which gave us 3. Looking at this next example, 8 root 5 minus 7 squared, it's important to recognize that this is the product of 8 root 5 minus 7 and itself. So we still need to use the distributive property. First, we have 8 root 5 times itself. 8 times 8 is 64, and root 5 times root 5, or root 5 multiplied by itself, is simply 5. Next, we have 8 root 5 times negative 7. 8 times negative 7 is negative 56, so we have negative 56 root 5. Continuing to distribute, we have another negative 7 times 8 root 5, or another minus 56 root 5. And finally, we have negative 7 times negative 7, or positive 49. 64 times 5 is 320, and 2 copies of minus 56 root 5 give us a total of minus 112 root 5. Adding 320 and 49, we have our final answer of 369 minus 112 root 5. In example 4, let's begin by distributing like we did in example 3. Notice that we have the square root of 38 plus the square root of 29 times the square root of 38 minus the square root of 29. So we first have 38 times itself, and we could write this as root 38 squared, or simply 38. Next, we have the square root of root 38 times the square root of negative 29. And then a positive root 29 times a positive root 38. These two middle terms cancel each other out and simply become a 0. And finally, we have root 29 times negative root 29, or negative root 29 multiplied by itself, which is simply negative 29. So what we are left with is simply 38 minus 29, or positive 9. This is the multiplication of two conjugates. We have the root 38 plus root 29 times root 38 minus root 29, and the result was 38 minus 29. Whenever we multiply two conjugates together, we have this result. A plus b times a minus b is a squared minus b squared. In factoring, we referred to this as the difference of squares. Let's try out this property on the next example. We have 7 root 10 minus 6 root 6 times 7 root 10 plus 6 root 6. We have a minus b times a plus b. So we know we'll have a result of a squared minus b squared, which in this case will be 7 root 10 squared minus 6 root 6 squared. To simplify 7 root 10 squared, consider that 7 squared is 49, and the square root of 10 squared is simply 10. To simplify 6 root 6 squared, we have that 6 squared is 36, and the square root of 6 squared is simply 6. So we have 490 minus 216, or 274. This property will also help us out when we are dividing. Before we can divide, we need to understand the process of rationalizing the denominator. This is the process of rewriting an expression without a radical in the denominator. Let's take a look at example 5. We first have the square root of 70 divided by the square root of 3. It is not proper to leave a radical in the denominator, so we need to multiply by the right version of 1 and leave us without a radical in the denominator. We know that root 3 times root 3, or root 3 multiplied by itself, is equal to 3, which is an expression without a radical. So let's multiply this quotient by root 3 over root 3. Now when we multiply, in the numerator we have root 70 times root 3, or the square root of 210. And in the denominator we have root 3 times itself, or simply 3. Now we need to think through if we can simplify the radical 210. I'll take a quick look at the prime factorizations of 70 and 3. 70 is equal to 7 times 10, or 7 times 2 times 5. And 3 is already prime. That means that 210 is equal to 7 times 2 times 5 times 3. Notice that this prime factorization does not have any repeats, so it is not divisible by any perfect squares. This is as simple as this expression will get. Let's take a look at 2 root 20. We again need to rationalize the denominator, but it's helpful to notice that root 20 could be simplified first. Root 20 is divisible by the perfect square 4, so this is the square root of 4 times 5, or 2 divided by 2 root 5. And now that we have a 2 in both the numerator and the denominator, this expression simplifies to 1 over root 5. Now we still need to rationalize the denominator, and we'll do that by multiplying the numerator and denominator by root 5 over root 5. This gives us 1 times root 5, or root 5 in the numerator, and root 5 times itself, or simply 5 in the denominator. And now there's no longer a radical in the denominator. Let's look at some slightly different examples. In example 6, we have 2 terms in the denominator. Let's think what we could do so that there's no longer a radical in the denominator. We know that root 5 plus root 3 multiplied by its conjugate, root 5 minus root 3, is equal to root 5 squared, or 5, minus root 3 squared, or 3. In other words, multiplying this denominator by its conjugate gives us a result with no radical. So we'll multiply by root 5 minus root 3 divided by root 5 minus root 3. This gives us root 15 times root 5 minus root 3 in the numerator and simply 2 in the denominator, or 5 minus 3. Distributing in the numerator, we first have root 15 times root 5, or the square root of 75. Then we have the square root of 15 times the negative square root of 3, which is negative square root 45. Simplifying the square root of 75, we recognize that 75 is divisible by the perfect square 25. So we rewrite this as the square root of 25 times 3. And we'll rewrite the square root of 45 as the square root of 9 times 5. The square root of 25 is 5, so our first term in the numerator is 5 root 3. The square root of 9 is 3, so the second term in the numerator becomes negative 3 root 5. And this is all still divided by 2. Now we have rationalized the denominator. We have rewritten the original expression so that there's no longer a radical in the denominator. Let's take a look at one last example. We again need to rationalize this denominator with 2 terms. And we will again use the method of multiplying the numerator and the denominator by the conjugate of the denominator. In this case, that's 2 root 3 plus root 5. In the numerator, we now have the product of 8 root 3 plus 3 root 5 and 2 root 3 plus root 5. And in the denominator, we have 2 root 3 squared minus root 5 squared. Distributing in the numerator, we first have 8 root 3 times 2 root 3, or 16 times 3. Next, we have 8 root 3 times root 5, or positive 8 root 15. Next, we have 3 root 5 times 2 root 3, or positive 6 root 15. And finally, 3 root 5 times root 5, or 3 times 5. In the denominator, we have 2 root 3 squared. 2 squared is 4, and root 3 squared is simply 3. And we have a negative root 5 squared, and root 5 squared is simply 5. Continuing to simplify, in the numerator, we have 16 times 3, or 48. Positive 8 root 15 plus 6 root 15 for a total of 14 times root 15, and 3 times 5, or positive 15. And in the denominator, 4 times 3 is 12, so we have 12 minus 5. Finally, 48 plus 15 is 63, so we have 63 plus 14 times root 15 in the numerator, and 12 minus 5, or 7, in the denominator. Now that we've fully simplified the numerator and the denominator, notice that both terms in the numerator are divisible by the denominator 7. That is, we have 63 divided by 7 plus 14 root 15 divided by 7, which we can simplify as 9 plus 2 root 15. Now we have rationalized the denominator and fully simplified the resulting expression. That will conclude this lecture video where we learned how to multiply and divide radical expressions.